Few people liked E.T. I think what else there was. Xenomorphs. No one really likes Xenomorphs. I don't know if that's like too old or something.
Okay, wait, hold on.
Maybe it's the people who take 110. They don't want to think about Xenomorphs. They want to think about fuzzy teddy bears.
Yeah, I was gonna say it's probably because they're scared of xenomorphs more than anything.
Which is fair. Anywho, that's looks like we have our quorum. So just a few notes. A few of you have asked for extensions on the spectroscopy project. I'm very okay with that. And I've extended it to Monday. If you have not asked and you need that, let me know and I will add you. But if you do not ask, I will assume that you are turning it in tonight. So that's kind of the way I operate. I am fine with giving extensions, but I need people to ask for them. If you have not signed up for a final presentation, please do that soon. And if you do have a topic, please try to get it in here. Some of you have emailed me what your topics are, and I have forgotten. So just so we can make sure that we don't have anything that's too closely overlapping anywhere. Because there's only so much I can keep straight in my brain. Yeah, those will start next week. The other note on those, there won't be like participation points. I will have you guys submit a little bit of feedback. But the main reason to attend, besides supporting your peers, is that the last 2 questions on your final will be taken from the presentation. So I'm putting together your final. It will look similar to the midterm, except there will be 6 questions on stuff I have covered, and then 2 questions where you will have a list of 1 question per presentation, and you will pick 2 of them to answer that are not your presentation. So kind of semi-similar to, I think, what Andrea and Nathaniel did when I was around. So just trying to keep that similar structure. Any questions about anything happening? Cool alien movies that we should all watch?
Arrival.
I didn't think of that. Yeah, that's a good one. I don't those aliens don't have names though, do they?
They're called, well, the species doesn't, but they're called Abbott and Costello in the movie.
They draw pretty pictures.
Good one. Okay. Speaking of aliens, I don't know. Local volume. It's a segue. So today we're going to talk a little bit about the galaxies within our local group and why studying them is important for understanding extragalactic astronomy. And I'm going to be totally honest with you guys. The local group is cool. I have been kind of dreading this presentation because it's not my favorite thing to talk about, even though I just wrote a proposal for why we should stare at the LMC. But this is just, I struggle with this topic a little bit more. When I took this class, I think Nathaniel spent like 3 weeks talking about the local group, and I think I slept through most of it. I'm not 100% sure. But so I'm going to try to make it, I like talking more about why we should research these things and what we can learn from them. So I'm going to try to bring that in. But if I'm a little less excited, that might be why. I'm sorry. I'm going to do my best. High energy. It's here. There's coffee in this today. So, usually it's just water. But to kind of explain why we want to study the local volume is that for the most part, these are our nearest neighbor galaxies. So they're galaxies that are close enough that we can observe structure, we can observe individual stars, individual star-forming regions, different environments, isolated environments. So we can get a lot of information that we can then use to calibrate things like star formation rate indicators in other galaxies, or measurements of stellar mass, where we can actually look at Andromeda and say there are 100 stars in this circle. What colors are we seeing? Because we can actually count those stars. So that's kind of the big reason to study the local volume, is that, yeah, we're near enough galaxies that are close enough that we can really see details that you just can't observe anywhere else in the universe. The other big thing we can do with the local universe that you can't do anywhere else is that we can get a statistically significant sample of faint dwarf galaxies. So I will talk a lot more about dwarf galaxies today, but if we want to actually know how many dwarf galaxies there are in a given volume, the only place we can really do that is within our local group. If we look even at the nearest clusters, it's going to be very hard to observe faint dwarf galaxies because they are so faint. So it's just hard to see them no matter what. So if your cosmological simulation needs to know how many dark matter halos there are in a given area, studying the local universe is going to be a really good way to get that. The last thing is that despite all of these local universe galaxies being approximately the same age as the Milky Way, because they're right next door, so the light travel time is millions of years instead of billions of years, and being in a pretty similar environment in terms of the universe, the local universe galaxies have some pretty different properties. So understanding why that is, understanding those different properties, how we get these different properties, can help us understand galaxy evolution. So this is why we should actually study this and why I should care and not dread this, but it is actually useful to understand. The next thing I want to talk about is how we define the local group. So the local group is the 38 galaxies that are in 1 megaparsec of the Milky Way. We can define it kind of both by this like 1 megaparsec boundary, but it's also all of the galaxies that seem to be gravitationally bound to the same center of mass and that are all moving together in the same local flow. So these all have kind of similar motion, seem to be around the same center of mass, which is between the Milky Way and Andromeda, and we're all kind of moving towards this thing called the Great Attractor. So the Milky Way is in this group of galaxies down here. Our closest cluster is the Virgo cluster. We are moving towards the Virgo cluster. And then from the Virgo cluster, we seem to be going towards this thing called the Great Attractor in the Centaurus cluster. I don't think we know exactly what it is, but it's large and probably massive and in this supercluster around the Centaurus cluster. Within our local group, there are 38 galaxies that we have measured, 3 large-ish galaxies, and then 35 dwarf galaxies. So we are really not in we are not in a cluster, we are not in a supercluster. Clusters are hundreds of galaxies. That's why we call it the local group, not the local cluster, because we are kind of at the edge, which kind of makes sense. We're a disk galaxy, or the Milky Way is a disk galaxy, and disk galaxies tend not to be found in clusters. So the fact that we are not in a cluster is maybe not entirely surprising. So my plan for today is I'm going to kind of run through a few properties of all the galaxies in our local neighborhood or our local group, and then talk a little bit about why studying them, a little bit more about what we can learn from studying them, and then let you guys play with some of the data from this. So it'll be not programming stuff, just kind of answering questions, but looking at some of the really pretty pictures we have and thinking about how we can use those to answer questions. So I'm going to dive into talking about our satellites and then the 3 big galaxies and then the dwarf galaxies. Before I do, any questions about why we study the local universe or what the local group is? Okay. So our 2 satellite galaxies are the Large and Small Magellanic Clouds. They orbit the Milky Way and are slowly being cannibalized by the Milky Way. One of the ways we can see that that must be the case is that there's this stream of gas behind the LMC and the SMC that seems to be trailing them, that's being pulled into the Milky Way over time. And the way we observe this gas, what's being shown here is we observe it by looking at quasar absorption lines. So this gas, pretty inert, it's not going to be emitting much on its own, but if light from a very distant quasar passes through it, we will see absorption lines. So we can use those absorption lines from the quasars to measure the locations of this gas falling into our galaxy. I don't talk about it much anywhere else, but by looking at kind of streams, stellar streams around the Milky Way, we've also been able to put together just the history of the Milky Way and how it has eaten galaxies in the past. So the Magellanic Stream is one stream that we observe. There are others, but our large and small Magellanic Cloud seem to be our only two existing satellite galaxies at this point in time. Sorry, that's I will get to that, sorry. So this is my little side note story that I had to throw in here. If you are thinking of going to grad school, this will all make sense why there's an echidna in this in a second. If you're thinking of going to grad school, there are 3 ways you can get paid as a grad student. So it's just a little PSA. You can TA, which is what most grad students do for their first 2 years. So then you're being paid by the department to teach. You can get paid by your advisor. So if your advisor has money to do research through a grant, they can pay you to do that research. Or you can do what I did, which is you can get your own grant. So you can apply to NSF or NASA or a program within whatever university you are at and get your own funding. The nice thing about that is that you get to choose which conferences you go to. So when my advisor gave me a list of conferences, one of them happened to be in Sydney. And I was like, this one, this one is the one I am going to. It is in Sydney in February. It's going to be warm there. And if you fly for 16 hours to get to a conference, you're going to stay afterwards. And that is how I took the best picture I've ever taken in my life. And I have to throw it in somewhere everywhere. So echidna backpacking in Tasmania after that conference, but also has to do with this presentation because the large and small Magellanic Cloud you can only see from the southern hemisphere. And that was my first time to the southern hemisphere. So I got to see the large and small Magellanic Clouds and an echidna and a wallaby, lots of wallabies, and some paddy melons, and it was great. So that's, if you can get your own funding, you get a little bit more freedom. So it's something to think about, but not now, obviously. Okay. So little tangent, sorry. I have to put that picture in everywhere. But now back to thinking about these dwarf galaxies. Our bigger satellite galaxy is the Large Magellanic Cloud, or the LMC. It's about 50 kiloparsecs from the Milky Way. We can measure these distances using Cepheids within the LMC. It's only 14 kiloparsecs across. Milky Way is closer to 50 kiloparsecs across, so very much a dwarf. And it's about 10% as luminous as the Milky Way, so very small. The really cool thing about the LMC is that it has a pretty low metallicity. So it's got a metallicity of about 0.5 Z solar, so half the solar metallicity. So it's a really nearby galaxy that doesn't have very many metals. So we can use it to kind of understand how having no metals affects measurements of star formation rate and other stuff. So you can kind of see in this image, they're pointing out some of the star forming regions and other exciting things in the LMC. You can specifically, this guy down here is the Tarantula Nebula, which is a massive star forming region in the Large Magellanic Cloud. There's also Bean Nebula up here, but there's just a lot. We can see these individual star forming regions, and we can see how do our indicators of star formation rate like FUV and IR still work if you have an extremely low metallicity galaxy, which is great if we want to measure star formation rate in the early universe when everything is low metallicity. So the other thing the LMC has taught us, which you might have heard already, is that Cepheid period luminosity relationships depend on metallicity. So by looking at the LMC, we can measure these individual Cepheids, and we notice that the Cepheids in the LMC seem to have a slightly different period luminosity relationship than those in Andromeda or the Milky Way. And that tells us that we have to be a little careful with our Cepheid distance indicator, because it will change if you are in a very low metallicity star. And one of the ways we know that is because we are able to look at the LMC. So the LMC, at least, is pretty cool. It does have, despite being irregular, it has some rotational motion, but not much structure. Dwarfs tend not to have a lot of structure just in general, so not entirely surprising. The other dwarf galaxy in the Milky Way, or satellite galaxy of the Milky Way, sorry, is the Small Magellanic Cloud. In this image, you can kind of see Small Magellanic Cloud is kind of trailing the Large Magellanic Cloud. So we think that there's a possibility that they used to be one larger dwarf galaxy that's being pulled apart by tidal forces from the Milky Way. We're not really sure though. It's even smaller than the LMC, only has a mass of about 6.5 times 10 to the 6 solar masses, so pretty dang small. But the cool thing about the Small Magellanic Cloud is it's even lower metallicity, so it's got a metallicity of about 1/4 Z solar. So again, just good for studying nearby where we can resolve individual stars. Low metallicity environments. Besides that, there's not a ton going on in the Small Magellanic Cloud. We've seen it has a very large number of X-ray binaries, which might be a sign that there's still some amount of continuous star formation, but there doesn't seem to be much. Because we don't see a lot of those other, like the really bright star forming regions that you saw in the LMC in the previous slide. The other thing, last thing I'll say about the large and small Magellanic Clouds is there's some question as to whether or not they have supermassive black holes in their center. There's still kind of arguments about whether or not they do. So trying to understand what the limit is on dwarf galaxies having these supermassive black holes, these are places where we can really look for those and try to find them. There's a limit on the last paper I saw, there was a limit on the size of a supermassive black hole in the center of the LMC, where they're saying it couldn't be bigger than, I think, 10 to the 4th solar masses. I don't quite remember, don't quote me on that. But so we have kind of limitations on the amount of mass in a supermassive black hole in the center of these, which just, again, provides an interesting laboratory to kind of study galaxy structure in these nearby dwarf irregular galaxies.
Is it possible they just have a normal mass black hole in the middle since they're dwarfs?
So they definitely have black holes. The question, I think what would be interesting is if they had intermediate mass black holes, since we haven't been able to find any of those as of yet. There's kind of the black hole problem is we have one stellar mass black hole, and we have million stellar mass black holes, and there doesn't seem to be anything in between. So if they have those, that would be interesting, and I think that's possible since we just have this upper mass limit, but I am not an expert on that at all, and I think the jury is still out. Good question. So the kind of stepping one more step in distance, the only big galaxy or similar size to the Milky Way galaxy in our local group is Andromeda. It's about 2.5 million light years away, or 760 kiloparsecs-ish. We can get this distance using Cepheid variables because we can resolve individual stars in Andromeda, which is neat. It's similar in size to the Milky Way, possibly a tiny bit smaller, but not much, with a stellar mass of about 1.5 times 10 to the 12th, or a mass, sorry, not a stellar mass, a mass of 1.5 times 10 to the 12th solar, and a radius of about 22 kiloparsecs. Kind of fun things about Andromeda. It seems like a fairly normal-ish spiral galaxy, but it does have some sort of ring potentially in the center, which might be a sign of some sort of collision in its past. So maybe something passed through and kind of sparked star formation in this ring in the center of Andromeda. And I put in the light year distance because I always use this when I do public talks because people think in light years, not parsecs. And it's always fun to show pictures of Andromeda. Only astronomers think in parsecs, unfortunately. The last large-ish galaxy in our group is Triangulum, or M33. So it's a gravitational companion of Andromeda, smaller than the Milky Way and Andromeda by quite a bit, a radius of 17 kiloparsecs. So 7 kiloparsecs less than the Milky Way, 4-ish less than Andromeda, 4 or 5 less than Andromeda. Mass of around 5 times 10 to the 10 solar masses. I saw some arguments as to what this exactly is, so I'm not sure how great of a measurement we have of this mass that I could find easily before this class, sorry. And it's around the same distance as Andromeda is away from us, 794 kiloparsecs away. Because it's a gravitational companion of Andromeda, this does put the center of mass of our local group closer to Andromeda than the Milky Way, because the other big galaxy in our local group is closer to Andromeda than the Milky Way. Another fun thing about this galaxy, is it has the biggest star forming region that we have seen in our local group. So this is NGC 604, which is a star forming region in Triangulum, about 40 times the size of the Orion star forming region. So the Orion stellar nursery is kind of our best large nearby star forming region, so it gets used as scale. This is 40 times larger than that. So cool, cool for seeing kind of extreme H2 bubbles and star formation. You see those little pockets stuff. And you can see all of the red emission from H alpha. Anyways, it's pretty. So those are our large galaxies and the Milky Way's dwarfs, or Milky Way satellites, sorry. Any questions so far? So the rest of the 33 galaxies in our local group are all dwarfs. LMC and SMC are also dwarfs. So this is the 35 out of 38 are dwarfs, or they must count 32 more galaxies. I think I missed 35. Yeah, okay, sorry. Triangulum, Andromeda, Milky Way are not dwarfs. The rest are all dwarfs. I can count. The SMC and the LMC are both dwarf irregulars. A lot of the other of these 33 are dwarf spheroidals and dwarf ellipticals, which I will talk about. I'm not going to go through all 33, obviously, because that would be horrible. If you want to look up information on any one, I think the paper I sent has a little bit about each one. Big thing for dwarfs, if you're less than a mass, if you have less of solar mass, if your mass is less than 10 to the 8 solar masses, you are a dwarf. So that's kind of the hard and fast rule. If you're below 10 to the 8, you are a dwarf. So on these graphs, log m 10 to the 8, these are going to be dwarfs. They are also pretty dang faint, which looking at them, how you can tell there's a galaxy, it's kind of amazing. And this is where things like the Dragonfly Array and the Dark Energy Survey are coming in to help us identify these really small dwarf galaxies. So the dwarf irregulars, this is another one besides the LMC and the SMC. This is IC 1613 in this image. We can kind of think of irregulars as extremely late type spirals. So SA is early type spiral, SBD would be late type. These are kind of like taking that to another extreme. They can have some amount of rotational motion that we measure with the H1 gas. So same way you guys did with NGC 7331, but now just looking at the 21 centimeter line in these irregulars to see that there is at least some organized motion despite them just looking kind of blob-ish. They, like I said, masses less than 10 to the 8 solar masses. They can be satellites of bigger galaxies like the LMC and SMC, not always, but tend to. And any type of dwarf, including these, are going to be difficult to observe outside of the local group. Dwarf irregulars do tend to have some amount of sustained star formation. So irregular galaxies in general tend to have fairly high star formation rates for their mass, but the dwarf irregulars are kind of unique within the dwarfs of having this kind of continuous star formation that we don't see in other dwarf galaxies necessarily. So the other two types, dwarf ellipticals and dwarf spheroidals, are both small spherical dwarf galaxies. The dwarf ellipticals tend to be more compact. There's kind of a bit of an argument about whether or not dwarf spheroidals and dwarf ellipticals are two different categories or if they're the same thing. The main way of distinguishing between them is that ellipticals are more compact, spheroidals are more diffuse. So where that line is drawn, if there's even a line. This guy here is M32, which is a satellite of Andromeda. So you're seeing it kind of through the disk of Andromeda, which is why it looks prettier. Dwarf ellipticals tend to be kind of like ellipticals. They don't seem to have much gas, not a lot of recent star formation. Not always true. I think with ellipticals, they're pretty much always red and dead. Dwarf ellipticals, we do still see some that have gas and star formation, but overall trend, they seem to be similar to ellipticals. Dwarf spheroidals are, like I said, they're similar to dwarf ellipticals, but now we are more diffuse. So where M32, you could see there was a galaxy there. This is the Draco dwarf spheroidal. Is there a galaxy there? Apparently, yes, according to people who measure dwarf spheroidal galaxies. So these are very, very dim, diffuse spherical galaxies. This is where we're really kind of hitting that edge between what is a galaxy and what is a globular cluster as well. So the main thing that seems to be the distinguishing fact is that dwarf spheroidal galaxies have dark matter. Globular clusters don't. We can tell based on kind of the velocity structures of these dwarf spheroidals and also the fact that they exist around bigger galaxies without being torn apart, despite the fact that there is nothing there. Also, some dwarf spheroidals seem to have their own globular clusters. So they have globular clusters orbiting them, which would suggest that they are different things. These galaxies tend to be dark matter dominated, with a few exceptions. So like some of those dragonfly galaxies might be dwarf spheroidals just without dark matter, potentially. But for the most part, these seem to be galaxies that are dominated by dark matter, where we can find, again, we can find the radius and the mass by figuring out how much mass you would need to hold together these stars that are moving together around other bigger galaxies without just stripping the stars out. So how much mass does it need to hold these stars together? For the most part, I looked into how they find these because I looked at this, my notes definitely say, how the hell do they find one of these in it? Because I don't get it. But the idea is if you look for stars that are all in the same place, moving with the same velocity, so they have the same velocity properties, they have the same RA deck and distance properties. And they also will look at the color magnitude diagram, so they'll make HR diagrams of these things similar to as what you would do with a globular cluster to try to see if they have similar-ish ages and metallicities, with the caveat that if you're looking at a galaxy, there's going to be different ages and metallicities. So we're really pushing the boundary between what's a globular cluster and what's a galaxy, but these are defined as galaxies. They're probably the most common galaxy type in the universe, just because we expect there to be a lot of these really small dwarf galaxy dark matter halos forming in the early days of the universe. So figuring out exactly how many there are around us is important if we want to understand how many there are anywhere else in the universe, because we cannot see this if we are looking anywhere outside of the local group. So on that note, yes, those are kind of, so I'm not sure exactly what fraction of the 33 are each dwarf category. I think they're mostly spheroidals and ellipticals, but I don't know off the top of my head how many there are of each. But those are all of the galaxies in our local group summarized quickly. 3 big ones: Milky Way, Andromeda, M33. Milky Way has 2 satellites, LMC, SMC. Both of those are very low metallicity, which makes them cool. And then 33 dwarf, irregular, spheroidal, and ellipticals, with irregulars being semi-like disk galaxies and spheroidals and ellipticals being more like elliptical galaxies, just very, very small. Any questions on any of that? So the last kind of section of this talk for me is from me before you guys work a little bit on your own, is to think about what problems we can kind of address by studying the local universe galaxies. And the first big one that I have to mention is the missing satellite problem. And so this is something, if you're in astronomy for long enough, you will hear someone mention the missing satellite problem. It does not seem to be as much of a problem anymore, but it's this mismatch between the number of satellite galaxies we see, the number of low mass galaxies we see, and how many low mass galaxies we expect based on our models of the universe. So these dots and this solid line in this figure are cold dark matter and lambda cold dark matter models of how many galaxies per mass we would expect to see. And then the data points here are showing the galaxies within the local group, the number of galaxies in the local group. So we have number on our y-axis versus circular velocity, which is essentially mass, on our x-axis. So more massive, more numerous. And based on what we expect from models of cold dark matter is that we expect there to be a lot of kind of small small dark matter halos that form into galaxies and a few big dark matter halos that form into galaxies. So here we go. This is n of 1, 2, 3-ish. Maybe this is higher than I would expect. Maybe they're sticking a few other things in this bin with Milky Way and Andromeda and Triangulum. But I don't know exactly how these plots are made, but the idea is the big problem is the fact that there's this mismatch here, where we're not seeing the number of dwarf galaxies, the number of satellite galaxies in our local group, as we would expect according to all of our models. And there's been a lot of efforts to try to fix this problem. And there's a lot of different solutions depending on who you ask. Putting it together, it probably means it's not a problem anymore. The first kind of biggest solution is just faint galaxies are hard to see. Like what you can see looking at this, finding galaxies that look like Draco, the dwarf Dracospheroidal, is difficult. So there might be a lot of these really small things that we just haven't been able to detect yet. So trying to extrapolate, like what can we measure versus what do we measure? Maybe this is fine and you can just populate this area completely with that. Another thing that's possible that would be extremely hard to detect would be galaxies that are only dark matter. So if you have a dark matter halo that is just dark matter, which is possible, we have galaxies without dark matter, maybe there are galaxies without baryons, why not? Then it would be very, very, very difficult to observe. So we don't really have a good way of observing it yet, outside maybe some form of kind of gravitational lensing, but you have to know where to look, and if it's a dwarf galaxy, you're not going to be massive enough to get a lot of this gravitational lensing. So we don't have a way of detecting dark matter only galaxies. So you might be able to boost these a bit by saying there's some galaxies that we will just never be able to detect because they're dark matter only. So we can fill in this space by postulating that those exist. There's a few other solutions. We're also, as we get more and more detections, this seems to be less and less of a problem. As our models get better, so there's kind of two ways you can make your theory better. You can boost these numbers or you can lower these numbers. So you can lower this curve or you can boost these values. So some of these are observations getting better. Some of these are models involving more stellar feedback. When we look at large scale structure, we'll talk a little bit about the different ways we model the universe. And I think Rain is also going to talk about the illustrious simulation, which involves some stellar feedback and other feedback that can limit the size of galaxies. So we've seen that kind of top curve maybe has gotten lowered a bit since 1999 when that paper showed it to be where it was. But we can also, and we've also seen the number of dwarf galaxies increase over time as we do things like correcting for brightness limitations of telescopes. So saying there are probably this many faint things we are missing based on the number of faint things we have seen and just how much we have looked. And then also correcting for area limitations of surveys. So our biggest all sky survey right now is SDSS. And it has only observed 3% of the local volume. So it's limited both by being in the northern hemisphere, so it can only see in the northern hemisphere, and it also cannot see in the disk of the Milky Way. So anything that's in the disk of the Milky Way is going to be blocked by the Milky Way. So our best survey so far has only surveyed 3% of the local volume. So if you extrapolate, maybe you can get, boost these points up if you multiply them by 1.97 or something. There's also, some other ways that you can kind of destroy dwarf galaxies to maybe lower that theoretical curve as well. So if we assume that a lot of our dwarf galaxies have been tidally stripped or cannibalized over the past 13.4 billion years, maybe that top curve is too high for the local volume. So maybe we're just destroying all of the nearby galaxies and we shouldn't expect to see the number that we do. So a lot of possible solutions. We have dark matter only galaxies. We have limitations due to brightnesses of telescopes. We have limitations for surveyed areas of the sky. We have potential methods for destroying galaxies. We have corrections to models of lambda cold dark matter universes. The other thing I didn't say, another potential way you can solve this is that in theory, our velocities might be wrong too, because if we're assuming, if we think maybe this value is too low, maybe it's because we're not seeing those dwarf galaxies aligned, we're seeing them face on. So if you also take into account the fact that we're probably not measuring the maximum velocity for all of these dwarf galaxies, maybe that boosts some of these points up a bit as well. The point is, we've probably solved it. Kind of different measurements at this point show that we are finding the right number of galaxies, potentially even too many galaxies. So maybe we have now overshot and we have not a missing satellite problem, but an overabundance of satellites problem. But it depends on what model you look at and what observations you include. The dark energy survey is also going to specifically be looking for these. So it is possible that as the dark energy survey continues to work, we will find more and more. So it's not just the Dragonfly team out finding these ridiculously faint things. We also have a large telescope dedicated to it. So another thing we can study by looking at the local group galaxies is kind of trying to figure out a bit about galaxy evolution by measuring the very different star formation histories in all of these local galaxies. So what we see is despite, like I said, despite all being pretty much in the same environment, all of these galaxies we're seeing essentially at now in astronomy talk and extragalactic astronomy talk, at least, you know, only millions of years in the past, so now. So we're seeing them now, we're seeing them in the same environment. Despite that, large and small Magellanic Clouds have like no metals for some reason. Andromeda has this weird ring going around it. The Milky Way has its bar. Why are we seeing all these differences? So we can use the fact that all of these galaxies are pretty different to try to understand how galaxies form, what influences how we get different galaxy shapes, different star formation rates, different metallicities over time. It also tells us that your location does not determine your star formation rate, despite the fact that we find ellipticals pretty much exclusively in clusters. There are differences even in the exact same location. And because I didn't think I had mentioned this yet, we can kind of start to test the kind of differences between top-down and bottom-up structure formation. So top-down galaxy formation models say that we start with like a big pancake of gas and dark matter that fragments into lots of smaller galaxies over time. So you start with a big galaxy, you start at the top, your most massive galaxy. That galaxy breaks apart, and we end up with lots of smaller galaxies. Bottom up is just flipped. We start with lots of small chunky galaxies. Those merge together to form bigger galaxies. So those are kind of the two formation models for galaxies. We seem to think bottom up is better because that's what we see. We see Milky Way eating dwarfs. We see galaxies colliding and forming bigger things. But we also see things like the large and small Magellanic Clouds potentially being pulled apart to form two smaller galaxies. So by looking at the local universe, we can see that, okay, maybe we're not exclusively top down or bottom up. We're probably more bottom up, but there are situations where you can get bigger things breaking apart as well. So by studying the local universe, the local group, we can kind of start to answer some of these questions about galaxy formation. My last thing I want to point out is that when we fit models of the universe, if we want to get a statistically complete sample of galaxies, we can only really do that for the local group. So all of the models that we build are kind of dependent on observations to check them. So we want to build a model and then see that it actually replicates what we see. So for a lot of these models, it'll say, we're going to build a model of the universe, run it forward in time, and see how many dwarf galaxies you build, how many dwarf ellipticals, how many dwarf irregulars, how many big galaxies. And if you want to check your models, which model everything, whether it's faint or bright, it's helpful to be able to actually know how many dwarf galaxies you have. And like I said, we can only really know that with any kind of moderate amount of confidence if we look in the local universe. So this is the only place where we can be pretty sure that we're actually observing all of the galaxies in this kind of 1 megaparsec bubble. And that's sort of what I'm trying to show with this graph here, where what this is showing is kind of your magnitude brightness, your magnitude limit at different redshifts. So for low redshifts, for things really close, we can see fainter things are observable. As you get more and more high redshift, you're only going to be observing the bright things. So there's a really good chance that there are still a bunch of galaxies down here in this blank area. Each of these points represents a galaxy. I'm not exactly sure what the lines are. Maybe it's like a cluster or something. But the idea is that if there are faint things at a redshift of 0.2, we aren't going to see them, whereas at a redshift of 0.0, essentially redshift of 0, we will still see them. So we see to fainter objects when we look nearby, this magnitude limit really gets to be a problem even at like pretty low redshifts, around 0.3 even. Another cool thing that we can test with our models is we can look at the motion. So I wanted to show you this model of the motion, the local flow. So this is kind of from a paper where they're just showing the flow in the local volume. So they're going to show all the galaxies and then how they've been moving sort of for the past 13 billion years. So I think this is the great attractor, this red thing. The Milky Way, I think, is this green point here. So just a fun way where we're really seeing how galaxies move, understanding that kind of structure formation based on the velocities that, again, are easier to model with local volume kind of galaxies. So I'll also say, I talked about the local group. The local volume is slightly bigger. Obviously, you're seeing here 40 megaparsec kind of bubble. So we can do some of this same work with the nearby clusters, the Coma cluster and the Virgo cluster. We're not completely limited to just the 38 galaxies in our local group. These are still close enough that we can see them pretty well. I focused on the local group because we're not going to go through every galaxy in each of these clusters. That would be super painful. But also, if you want to study cluster environments, those are nearby clusters that we still can learn a lot from. So I think in summary, before I let you out to play with some of this data yourselves, we have our local universe galaxies. We can use them to study resolved stars in other galaxies to see how they're different, resolved star forming regions to test our methods for measuring star formation rates and other things when we can actually get other measurements of those besides actually count the stars, actually do that kind of work. See different environments within nearby galaxies to understand both galaxy evolution and how our measurements work. Test theories about the structure of the universe, test our models for the universe, looking at things like the missing satellite problem. And also, did I say other things? Yeah, and study just how galaxies might form over time by looking at how our local universe galaxies are different. So with this new data, our assignment for today is this local volume galaxies assignment, which has a little quiz, fairly typical, asking just some questions, and then also has some links to different data that I think are cool, including the FAT treasury. So this is the really amazing survey of Andromeda. I walk you through a teensy tiny bit of math for thinking about angular resolution for what we would see with Andromeda. This should look similar from the 170s. So nothing, but it's more kind of telescope observational stuff than I really want to dig into too much. But just thinking what we can get when we look at these local universe galaxies. And then a few other questions about the dwarf galaxies. But again, hopefully nothing too surprising. So I'm gonna open breakout rooms as I do. Are there any questions about this or anything else? Okay, well, it looks like we are gonna have plenty of time to do this today. I didn't want to talk about local universe galaxies. Sorry. So maybe we can come back at around 3:45 to really quickly talk through some of this together, and then wrap up for today. It's another couple minutes. I just wanted to quickly at least go over the first few problems. Last room is going to get booted in a second. Here we go. Okay, so I just wanted to, at least in the last 2 minutes, at least kind of make sure everyone was on the same page with the problems 2 and 3. So in problem 2, I asked for a resolution of Hubble. So that's going to be this equation. We just need to all be in meters. So 500 nanometers visible-ish, divided by the size of Hubble, which is 2.4 meters. So that's our -9 to get them both in meters. So what did people get? I've got my chat open. What did you get for the resolution of Hubble? Yeah. Similar to what Sabrina got, about 0.052-ish arc seconds. So then we can take that, and we have a triangle here where I have Andromeda. So I should maybe try to draw Andromeda. Andromeda has, if we're looking at a resolution of this angle of 0.52 arc seconds, we can plug that in here. We have a distance to Andromeda. And so as Ethan has mentioned to me, Ethan, this is going to be a linear size of about 0.19 parsecs. So just even if we consider how far apart stars are in the Milky Way, this is much smaller than that scale. So we're getting not only individual stars, but really, really nice resolution in this fat image. So that's the idea of how to get to that. This is the full zoom in, which is just really, really, oops, sorry, was not sharing. Look at that, look at those stars. So just really cool what they are able to do with this, to think about what we can learn when we have this good of resolution. And this is just me looking at the full JPEG. So if you really zoom in with a FITS file, you can get just kind of all kinds of cool data from this. So a fun thing to know that is out there if you want to really learn about kind of spatially resolved stars in another galaxy, thanks to 411 Hubble pointing, 7,398 exposures. So just one of these really kind of just big Hubble programs that give us a ton of data. So if you can argue that you deserve this much Hubble time, good for you. And then I also showed you this field of streams that just kind of shows less good resolution, but still some great data from SDSS showing the streams where we think there were dwarf galaxies that the Milky Way has eaten. This should get better with Gaia and LSST and all of these future things, but it's what we have right now and it's cool. The rest of these questions are just kind of little review of what I discussed in class. So if at least you got through question 4, that's good enough for today. I don't need to give you more work. You can submit and you'll get full credit. Just know that the last few questions are nice kind of review of what I expected you to take away from this lecture. So do those or not. And I will see you all on Thursday for my last lecture to you, where we're going to talk a little bit about large scale structure. So just the big makeup of the universe.